Greetings, ladies and gentlemen. My name is Zeren Shui. I'm a graduate student at the University of Minnesota, Twin Cities. My advisor is Professor George Karpis. Today, I'm going to present our work, Heterogeneous Molecular Graph Neural Networks for Predicting Molecule Properties. Predicting molecule properties based on their atomic composition and geometric structures are important in molecule screening and drug design. This problem can be solved by solving the many-body Schrödinger's equation. However, the closed-form solution to the many-body Schrödinger's equation is only available for simple systems. Researchers developed methods such as density functional theory to approximate the solution of many-body Schrödinger's equation. However, this approximation-based methods scales poorly with respect to the number of electrons. For example, it takes an hour for a DFT to compute a property of a molecule with 20 atoms. Recently, there's a trend in developing machine learning-based methods to predict molecule properties. These machine learning-based methods are orders of magnitude faster than DFT-based methods, and they are almost as accurate as DFT. Among the machine learning-based methods, graph neural network-based methods is attracting a lot of attention from the researchers. Graph neural network is a type of neural network model that computes low-dimensional embedding of each node as a function of its ego network of a certain depth. Here we give an example of a target node in the graph and its two-hop ego network. So the target node is marked as red, and the one-hop neighbors of it is marked as dark green, and two-hop neighbors are marked as light green. So graph neural network is composed of a stack of GNN layers. Each GNN layer aggregates feature information from a node's one-hop neighbors. Iteratively applying this operation propagates information to nodes that are several hops away. Here we give an example of the computation flow of two-layer graph neural networks. In the first layer, the target node aggregates information from its one-hop neighbors, and its one-hop neighbors aggregate information from their one-hop neighbors, which are the two-hop neighbors of the target node. And in the second layer, the target node aggregates information from its one-hop neighbors. Note that at this point of time, the one-hop neighbors already have information of the two-hop neighbors of the target nodes. By modeling message passing, graph neural networks can model complex interactions among atoms. Currently, existing GNN-based methods apply on graphs in which atoms are modeled as nodes. For example, in a distance graph, atoms are connected if the distance between them is less than a cutoff threshold. And in a KNN graph, each atom is connected to the k nearest atoms of it. And in the ball and stick model, atoms are connected by some abstracted chemical bonds. So in these methods, they mainly focus on modeling atom representations and interactions between atoms. They do not have an explicit characterization of many-body representations, interactions, and predictions. In this work, we're trying to explicitly model many bodies. In order to do that, we propose a novel molecule representation called heterogeneous molecular graph. Before we jump into heterogeneous molecular graph, let me first give a brief introduction to heterogeneous graph. So heterogeneous graph is a type of graph that contains different types of nodes and edges. So nodes and edges of different types usually have attributes that encode different information. Here's an example of a heterogeneous graph in the music domain. So this graph contains three types of nodes: songs, which is marked by yellow, and people, which are marked by blue, and words marked by grain. And there are 4 types of edges: road, sand, friends, and wall. So heterogeneous molecular graph also have like different types of nodes and edges. So a heterogeneous molecular graph is built on the basis of a distance graph. A p-body or a node of order p in a heterogeneous molecular graph is a p-clique of the base distance graph. Each node in a heterogeneous molecular graph is associated with a discrete feature which encodes its atomic composition, and a continuous feature which encodes its geometric structure. In a heterogeneous molecular graph, 2 nodes, I of order P and J of order Q, are connected in 2 scenarios. So the first one, if I is a subgraph of J, then I is connected to J. And the second one, if I and J are of the same order and they share P minus 1 atoms, then they are connected. So in the second scenario, the edges are associated with an edge feature that encodes the geometric relation between the 2 nodes. For example, like angle between the 2 bodies, or dihedral angles between 3 bodies. So below we give an example of a distance graph and the corresponding heterogeneous molecular graph of order 2. So in the heterogeneous molecular graph, there are 2 types of nodes, like 1 bodies and 2 bodies. And there are 3 types of edges, like edges between 1 bodies, edges between 2 bodies, and edges between 1 bodies and 2 bodies. So edges between 1 bodies and edges between 2 bodies are associated with edge features that depicts their geometric relationships. In this work, we use radial basis functions to convert distance and angles to real valued vectors. In order to leverage the rich information stored in heterogeneous molecular graph, we propose heterogeneous molecular graph neural network, HMGNN in short. So a heterogeneous molecular graph neural network consists of 4 core components: an input module, an interaction module, an output module, and a fusion module. The input module converts raw nodes features to latent node embeddings. The interaction modules are designed upon message passing framework for nodes to send and receive messages from its neighbors of different orders. And the output module kind of takes the final node embeddings and kind of output one prediction for each node. The fusion module takes the final node embeddings and compute a global molecule representation and use the global molecule representation to weight the prediction of different orders. Since the input module and the output module are quite standard and simple, we will just skip them, and let's delve in depth into the interaction module and the fusion module. So the interaction module takes information from neighbors of different orders, and in order to do so, it needs to maintain like one set of parameters for neighbors of each order. And when it receives messages from different orders, it first sum all the messages from the order to be the message of that order, and then it concatenate messages from all the orders to be the message to the node, and then it pass the message through several fully connected layers and residual layers, and then it uses an residual connection to connect the to add the message to the node feature. And after that, it kind of passed the node feature through a residual layer to be the final output of the module. We stack interaction modules for each order to capture information that are hops away. The fusion module takes the final node embeddings computed from the interaction modules and kind of organize them into a global molecule representation. So it first sums all the node embeddings of each order to be the representation of that order, and it concatenates representation of all the orders to be the global molecule representation. Since the node embeddings of different orders are computed from different parameters, we pass the global molecule representation through a batch norm to unify their distribution. And after that, we pass it through a attention mechanism to compute the weights of different orders. The final prediction of a molecule by HMGNN is computed as a weighted summation of the prediction of different orders. So the weights alpha is the attention weight computed from the fusion module, and the YPs are a prediction of different orders. This formulation is motivated by the many-body expansion of the energy of m-particle systems. So in the many-body expansion, it is assumed that the local contribution to the energy decreases with the order of many bodies. In our experiments, we demonstrate that our fusion module aligns pretty well with this many-body expansion assumption. So since the final prediction of HMGNN is the weighted combination of predictions of different orders, naive regression loss may cause gradient vanishing issues for parameters of orders with like small weights. And as a result, these parameters will lose their prediction utilities. So to avoid that issue, we cast the prediction of each order as a prediction task and train the model using a multitask learning loss. With this formulation, we kind of force the prediction of each order to be as accurate as possible, and then we use the fusion model to combine this result, and so that the final prediction is more accurate. Experimental results shows that this multitask learning framework is playing a critical role in the design of our HMGNN model. We compare our HMGNN model with current state-of-the-art methods. So especially machine learning and graph neural network based methods on a well-known benchmark like the QM9 dataset. Here we report the mean absolute error of all the methods. So HMGNN1 refers to the prediction accuracy of order 1 of HMGNN. And HMGNN2 refers to the prediction of order 2, and HMGNN is the weighted combination of order 1 and 2, which is like final prediction. So from this table, we can see like HMGNN sets the new state-of-the-art on 9 out of 12 target properties. And the weighted combination HMGNN outperforms any of the standalone predictions. And this demonstrates the effectiveness of our fusion model. We conduct ablation studies on 2 targets from the QM9 dataset by experimenting with 3 variants of the HMGNN model. So the first variant trains HMGNN with the naive loss instead of the multitask loss. As a result, we can see that order 2 lost its prediction power, and the performance of order 1 also degrades. The second variant remove edges between nodes of different orders. And as a result, we can see that the performance degrades, which demonstrate the importance of interorder message passing. And the third variant trains HMGNN with only order 1, which means it removes all many-body related modeling, like many-body representation, interaction, and prediction. So the performance degrades, and what we want to note here is that if we compare this variant with the one that is trained with the naive loss, so in the one with naive loss, even the second order lost its prediction power. The performance of the first order is still better than this one variant that is trained with only order 1. And that demonstrates the utility of the modeling of many-body representations and interactions. Here we show the attention weight of order 1 prediction. Since we are only experimenting with HMGNN for up to order 2, the attention weight of the second order can be obtained by 1 minus the attention weight of the first order. So we can see from this 4 figures, so in the prediction of these 4 targets, the prediction of the first order dominates all these 4 targets. And this aligns perfectly with the convergence assumption of the many-body expansion. At the end of the talk, we want to highlight so explicit modeling of many-body representation, interaction, and prediction is important for molecule property prediction tasks. And second, experimental results demonstrate that HMGNN achieves state-of-the-art performance in 9 out of 12 prediction tests on the QM9 dataset. And finally, the multitask learning framework works pretty well with the architecture of HMGNN and the many-body expansion of molecule properties. Thank you.